Welcome to today's explainer. If you think about the iron pumping through your veins right now, it's literally keeping you alive. But what if I told you that very same element is actually a microscopic ticking time bomb? Today, we're exploring how life navigates the incredibly razor-thin line between essential nourishment and toxic overload. I absolutely love unpacking topics like this because it forces us to look closely at the epic microscopic survival battles happening right under our feet. We're looking at a story that combines chemical warfare, communal living, and the desperate quest for one of the universe's most important elements. Let's dive right into this central paradox. Iron is absolutely crucial for things like cellular respiration and DNA repair. For almost all living cells, from the tiniest bacteria to us humans, iron is a totally non-negotiable transition metal. It transports oxygen in our tissues, it handles electron transfer during respiration, and it essentially keeps the whole biological engine running. But here's the catch. It is incredibly volatile. Relying on iron for life is honestly a lot like trying to power your house with a controlled stick of dynamite. See, when iron builds up too much in our tissues, it causes severe oxidative stress that literally destroys the cell from the inside out. Basically, too much free iron completely wrecks a cell's delicate balance and sets off this terrifying chain reaction of toxic molecules. We call them reactive oxygen species. Think of it kind of like biological rusting. If a cell gets greedy and takes in too much iron, it triggers its own messy iron-dependent demise. Scientists call this ferroptosis. It's a spectacular and totally lethal system failure. But out in the real world, in the soil, life faces the exact opposite threat. While iron is actually one of the most abundant metals in the Earth's crust, it is almost completely inaccessible to organisms living in oxygen-rich dirt. It's this incredibly frustrating, almost tragic irony for a microbe. The iron is everywhere. It's locked up in oxides and hydroxides all around them. But because of the oxygen in the environment, those iron compounds are stubbornly solid. Imagine starving to death while locked inside a fully stocked grocery store, just because all the food is sealed inside impenetrable titanium vaults. That is the daily reality for soil bacteria. To give you an idea of just how scarce this bioavailable metal really is, iron in the soil has a solubility of 10 to the negative 18th molar at a neutral pH. What does that actually mean in plain English? It means it's effectively zero. It's literally like trying to find one specific single grain of sugar hidden somewhere inside an Olympic-sized swimming pool. So these soil bacteria, they're surrounded by this endless buffet of iron, but they are completely trapped behind a glass wall of chemical insolubility. Which brings us to the star of our explainer, a tiny, soil-dwelling bacterium called Bacillus subtilis. This little guy has to pull off a miraculous, high-stakes balancing act every single day. It has to acquire just enough of this highly insoluble metal from the dirt to divide and thrive, but not so much that it accidentally triggers oxidative stress and sudden cell death. It's walking a microscopic tightrope every single second of its existence. As researchers studying this have pointed out, these terrestrial organisms are living in an iron-rich world where they just can't access the iron. So how do they cope? Well, nature came up with a beautifully coordinated dual-action strategy to solve this conundrum. Let's look at exactly how these microbes manage to pick the lock of that titanium vault and save themselves from starvation. Part 1 of this biological lockpick involves something called siderophores. In our specific bacterium, the molecule is known as bacillibactin. Think of these like microscopic claw machines that the bacteria send out into the dirt. Because these siderophores have an incredibly high chemical affinity for iron, they can actually outcompete the surrounding soil, latch onto those stubborn iron atoms, and pry them loose. Part 2 of the survival strategy is the biofilm. This is a sticky, protective layer that the bacteria literally secrete all around themselves. Now, you might just think of a biofilm as slime on a rock, but it is actually a highly sophisticated communal fishing net. It's a specialized, self-made environment where the bacteria pack tightly together. And, as we'll see in a minute, this physical structure is completely non-negotiable if they want to get that iron. So here is how this incredible trap is actually sprung. First, the bacteria realize they're running dangerously low on internal iron. So they spend their precious, dwindling energy manufacturing those bacillobactin claws and pump them out into the void. Then, the claws grab the iron from the dirt. Finally, that sticky biofilm matrix acts as a net to ensure the meal doesn't just wash away into the vast soil. The net catches the claws, and the claws hold the iron. The data shows us something absolutely fascinating around the mid-stage of their growth. There is this exact moment where the sharp drop in their intracellular iron completely stops. Right around 19 hours in, they flip a genetic switch. They're actively producing the cytophore claws, that biofilm fishing net is forming around them, and their internal iron levels flatline at a perfectly safe, constant concentration. They hit the ultimate sweet spot between starving and rusting. But before that stabilization happens, it's pure panic. The bacteria are in sheer survival mode. In those early stages, they aren't actually acquiring any new iron at all. Instead, they are desperately dividing by simply diluting their original internal iron stocks. A mother cell divides, and the daughter cells just split whatever iron was already inside the parent. They're frantically pumping out those claws during this time, but the iron hasn't made it back into the cells yet. They're literally living on borrowed time. To prove just how vital this teamwork really is, researchers put it to the test by creating mutant strains of the bacteria. They basically broke the system on purpose. They made one mutant that couldn't build the biofilm net and another that couldn't make the chemical claws. And the result? Well, if you lack either the claw or the net, you completely fail to grow. The mutant bacteria just collapse right at that critical mid-stage point. When measuring population growth, the healthy wild-type bacteria shoot right up, showing explosive and totally normal development. But those two mutant strains, they stay completely stagnant, just flatlining in the mid to late stages. Without the ability to complete that dual action strategy we talked about, they simply cannot acquire the iron they need. Once they exhaust those internal diluted iron stocks, their growth arrests entirely. Game over. This actually led to a massive revelation about the mutant that lacked a biofilm. It turns out, even if a bacterium can produce those cytophore claws, without the matrix net to trap the returning iron, the nutrients just drift away into the abyss. Researchers even tried artificially dumping loads of iron-loaded claws right onto these naked cells, assuming they just eat it up. But they couldn't digest them. Their growth only recovered by a measly 30%. So the biofilm matrix isn't just a house they live in, it's an active, absolutely vital part of their digestive system. Furthermore, the physical presence of the biofilm actually improves the chemical complexation of the iron. Basically, it helps the claws grip the metal tighter and faster. It is not just a passive knit. Testing showed that the unique microenvironment of the biofilm itself, the specific pH, the chemical gradients, all those tightly packed cells, it creates the ultimate arena for capturing this precious metal. It literally supercharges the claws. Now here's a crazy twist. It turns out you only need this net if the environment is still. This whole setup is unique to static, real-world soil conditions. If you take these exact same mutant bacteria and put them in a shaking liquid flask in a laboratory, they survive just fine. Why? Because the food is violently crashing right into their faces. But in actual static dirt, distance is deadly. The biofilm is evolution's brilliant answer to bridging that microscopic gap between a hungry cell and a stubbornly distant speck of iron. By working together, the chemical claws and the communal net allow the bacteria to achieve the holy grail of biology, redox homeostasis. They navigate the environmental extremes perfectly. They pull in exactly what they need to keep dividing, but their complex trap ensures they don't overaccumulate iron and accidentally trigger that toxic cell-shattering process of ferroptosis. It really is a stunning microscopic tightrope walk. As we wrap up today's explainer, I want you to consider this. Your own body is performing this exact same high-stakes tightrope walk right now. You might not be secreting biofilms into the dirt, but your cells are constantly juggling iron uptake to fuel your breathing, all while carefully preventing oxidative stress so you don't literally rust from the inside out. The rules of survival, it seems, are universal. So how is that delicate chemical balancing act playing out inside your cells at this very moment? I hope this gave you a brand new appreciation for the incredible ingenuity of life at the cellular level. Keep questioning, keep learning, and I'll catch you in the next one.